Okay, so this is Mod 7's Chapter 1 test. Numbers 1 and 2 are one-sided limits. So one-sided limits are evaluated the same as a regular limit. So first we would start with a direct substitution. A direct substitution of -3 would give us indeterminate form of 0 over 0. So look for some algebraic technique to simplify. In this case, we can factor the denominator. So we know x plus 3 better be a factor of the denominator, so we can cancel those terms. And now a direct substitution of -3 back into the simplified function would give us -1 over 5. On number 2, a direct substitution will give us a number over 0. Number over 0 tells us that a vertical asymptote occurs on the graph of the function at x is equal to 1. So the one-sided limits are going to be positive or negative infinity. Plugging in any value to the right of 1 will keep both the numerator and denominator positive. So the one-sided limit would be positive infinity. For number 3, to determine the limit as x approaches 0, we again have to look at one-sided limits. With a piecewise function, the one-sided limits are determined by the domain. So for values less than 0, we would look at the trig function. This is one of our special trig limits. So we know that limit to be 0. The limit as x approaches 0 from the right-hand side. We would evaluate the line at 0 and get a value of 0 as well. Therefore, the limit as x approaches 0 exists, and it is 0 as well. Alright, number 4. We plugged in any number to the left of 3 into the absolute value. So 1, 2, 0, any value less than 3. The absolute value would make that negative number positive. So to evaluate this limit, again, for a number less than 3, the absolute value takes the opposite of what's inside the function. These factors cancel to -1, and the opposite of -1 would be +1. So the limit as x approaches 3 is +1. Now a direct substitution into this function gives us another indeterminate form. So again, algebraically, we need to look to do something to simplify it. Okay, limit as x approaches 0 of this function in number 5. Direct substitution will give us 0 over 0. So what I'm going to do, separate the numerator into 2 separate fractions, and I can do that. This first function, so then we have a rule that says we can take the limit of each piece of the expression. The x's here cancel. This is our other special trig limit. Limit as x approaches 0 of sine x over x is 1. Limit as x approaches 4 of 4 is that. So 1 minus 4 would give us a value of -3. Okay, direct substitution again gives us 0 over 0. So what we're going to look to do, the numerator is asking us to subtract 2 fractions. So first I'm going to write the second term as 1 over 1. Then it identifies the common denominator for us to be 2x plus 1. So the first fraction doesn't need to be multiplied by anything. The second fraction multiplied by 2x plus 1 on the top and bottom. That denominator, the dividing by x, carries from the original. So limit as x approaches 0, 1, distributing the negative, and then dividing by x is the same as multiplying by 1 over x. The 1's cancel. Furthermore, the x in the top and the x in the bottom will cancel. So now we get the limit as x approaches 0 of -2 all over 2x plus 1, making a direct substitution of 0 in for x. We get the limit to be -2. Number 7, this should look familiar. This is the definition of derivative. Limit as delta x approaches 0. So expanding the binomial, square the first, double the product, square the last term. Then I'm going to distribute those negatives in the second terms. Okay, next step, distribute the 4. Plus 4 delta x squared. Okay, and then in the numerator, the x terms cancel, and each term that we're left with, we can factor delta x out of those terms. We're left with 8x plus 4 delta x minus 1. Don't forget, anything divided by itself is 1, so we have to keep that minus 1 as part of our simplified function. Now the delta x's cancel. Limit as delta x approaches 0. Now of this function, making a direct substitution of 0 for delta x, we get 8x minus 1. And now we know that to be the definition of derivative, so we can check our answer with the power rule. Find all values of c such that the function is continuous for all real numbers. Remember, continuity at a point, the function has to exist. The limit of the function has to exist. And lastly, the value of the function and the limit of the function, they're equal. Okay, so it's a piecewise function. We'll focus on finding the limit. Now where does the domain switch? The domain switches at c, which is the value that we're looking for. So for values to less than c, we would look at the quadratic function. Values greater than c, we would look at the linear function. So making a direct substitution of c into the quadratic and into the line yields those two equations. Now in order for the limit to exist, the one-sided limits have to be equal. Now this function is quadratic, so I'm going to move all the terms to the right-hand side of the equation. This is a perfect square trinomial, so it factors to 2c minus 5 quantity squared. And we can show that c is going to be 5 halves. Okay, number 9, sketch this function. To do so, identify the x and y intercepts, vertical and horizontal asymptotes if they exist. So x-intercepts occur when y is equal to 0, y-intercepts occur when x is equal to 0, vertical asymptotes occur when you have number over 0, and horizontal asymptotes are our limits at infinity. So in a rational function, to determine where the x-intercepts occur, we set the numerator equal to 0, so we get x is equal to 0. To find the y-intercepts, we replace all our x's with zeros. So the x and y-intercepts both occur at the origin. Vertical asymptotes come from where the denominator would be 0. Attempting to solve this equation for 0 gives us a not true statement, so no vertical asymptotes exist. Lastly, horizontal asymptotes, we find the limit at infinity. So the limit as x approaches infinity. Because the function has a square root in it, we have to look at both cases. Limit as x approaches negative infinity as well. So we can still use the technique of comparing the degree of the numerator with the degree of the denominator. If x is a positive value, then the square root of x squared is just positive x. And we get a limit of negative 2. As x approaches negative infinity, however, the square root of x squared simplifies to negative x, which gives us a horizontal asymptote at 2 as well. Alright, so as x approaches positive infinity, the horizontal asymptote will be at negative 2. As x approaches negative infinity, the horizontal asymptote will be at positive 2. And then we know our x and y intercepts are at 0. So just satisfying all the conditions, and we know no vertical asymptote exists, so that would be the sketch of the function. To sketch this one, same conditions. X-intercepts occur when the numerator is 0, so that occurs at negative 1. Y-intercepts occur when x is 0, so that gives us a y-intercept of negative 1/4. Vertical asymptotes come from where the denominator is 0. And then lastly, horizontal asymptotes, we can use our simplifying methods. This function is bottom heavy. The x squared is bigger than the x term, so the limit at both positive and negative infinity will be 0. So now putting all that together, x-intercept at negative 1, y-intercept at negative 1/4, vertical asymptotes at 2 and negative 2. The x-axis serves as the horizontal asymptote. Now you can use one-sided limits to determine the behavior of the function at the asymptotes. And you can verify that this is what the graph would look like. But all the conditions are satisfied. And that's it.